Hello friends, myself Dr. Amit Bagde, Assistant Professor in Sharad Institute of Technology, College of Engineering, Yadra, Karanchi. So this is the lecture number 2. So last lecture we are discussed about the motion or oscillations, and the different type of oscillations and motions. So today we are discussing about the differential equation of the simple harmonic motion. So this is the differential equation of the linear simple harmonic motion. So we know that the restraining force is given by that is F is equal to minus kx, where k is the force constant, x is the displacement of the body from the mean position. So you should know about the mean position and extreme position. Okay, but according to Newton's law, force is equal to mass into acceleration, that is F is equal to ma, but the acceleration is dv by dt, that is change in velocity per unit time. This is the acceleration. So the velocity is v is equal to dx by dt. So velocity is the displacement per unit time. This is the velocity, but we know that a is equal to d by dt into dx by dt. Okay, so this is the acceleration. D square x upon dt square is the acceleration. So as we know that f is equal to minus kx and f is equal to ma, this is Newton's second law. So but acceleration a is equal to dv by dt, this is change in velocity per unit time. Also the velocity v is equal to dx by dt. So a is equal to d by dt dx by dt. So a is equal to d square x upon dt square. Therefore, as we know that f is equal to ma, so f is equal to m into acceleration. Put this value in this equation, that is a is equal to d square x upon dt square. So f is equal to m into d square x upon dt square. Suppose this is equation number 3. So substituting equation number 3 in equation number 1, that is f is equal to minus kx. So f is equal to m d square x upon dt square is equal to minus kx. Okay, so d square x upon dt square is equal to minus k upon m into x, or the d square x upon dt square plus k by m into x is equal to 0. Suppose this is the equation number 4. Suppose this is equation number 4, d square x upon dt square plus k by m k by m into x is equal to 0. So put the value k by m is equal to constant. Suppose k by m is the omega, where omega is the angular velocity. Then equation becomes d square x upon dt square plus omega square x is equal to 0. Suppose this is the equation number 5. So equation number 4 and 5 are the differential equations of the linear harmonic simple harmonic motion. So we should note that the k by m is the positive quantity and omega square is the positive, but omega may be positive or negative. So d square x upon dt square plus omega square x is equal to 0 is the differential equation of linear simple harmonic motion. Another one is the expression for acceleration in linear simple harmonic motion. So this is the example. Suppose this is the mean position of the object, this is the right extreme position, and this is the left extreme position. So in this example, what is the value of a, that is amplitude, what is the velocity, and what is the displacement. So first, what is the value of acceleration? So this is the expression for acceleration. This is the example. Suppose r is the right extreme position, this is R is the right extreme position, L is the left extreme position, and O is the extreme position, and this X represent the displacement of the object. Okay, so the differential equation is the d square x upon dt square plus omega square x is equal to 0. So we already know that the A is equal to d square x upon dt square. So d square x upon dt square is equal to minus omega square x, or A is equal to put the value of A in this equation. Therefore, A is equal to minus omega square x. Suppose this is equation number 1. And A is equal to minus omega square x, where omega is the constant, is directly proportional to minus x, that is acceleration directly proportional to displacement. So this negative sign indicates acceleration and displacement are the opposite to each other. Maximum and minimum acceleration. So as we know that A is equal to omega square x. Okay, so case number 1. In case number 1, suppose x is equal to 0 and suppose x is equal to plus or minus a. These are the two cases. So in first case, at the mean position, we know that x is equal to 0, there is no displacement. Therefore, a minimum is equal to 0. Okay, at mean position. But at extreme position, suppose a is equal to plus or minus a, then a max is equal to plus or minus a into omega square. Okay, so a is equal to minus omega square into plus or minus a, or plus or minus a omega square. So this is the summary. This is the same example. L is the left extreme position, R is the right extreme position. In left extreme position, the displacement is x is equal to minus a. At mean position, the displacement is equal to x. At P, the displacement is x, and at point R, that is right extreme side, the displacement x is equal to plus a. So A max in left extreme position, maximum amplitude is equal to plus a omega square. Mean position, the value of amplitude A minimum is 0. At point P, the A is equal to minus omega square s, and A maximum is equal to minus a omega square. This is the right extreme position. Another one is the expression for velocity in simple harmonic linear simple harmonic motion. So this is the expression for velocity. This is a very simple expression. As we know that the acceleration is equal to dv by dt. So multiply and divide by this equation by dx. Then a is equal to dv by dx into dx by dt. But the dx by dt is nothing but the velocity, that is change in displacement per unit time. So a is equal to v into dv by dx. So as we know that is equal to minus omega square x. Therefore, put this value in this equation. So minus omega square x is equal to v into dv by dx, or v into dv, and this dx is multiplied to this minus omega square x. So v dv is equal to minus omega square x ds. If we separating the variables, then we get v dv is equal to minus omega square x dx. So integrate this equation. So integration of v dv is equal to integration minus omega square x dx. So this integration, so by using the formula, integration of x dx is equal to x by 2 plus c, where c is the constant of integration. So integration of v dv is equal to v square by 2 plus c. So v square by 2 is equal to minus omega square x square by 2 plus c. Suppose this is equation number 2, where c is the constant of integration. Then to find the value of c, this is the again same example. This is the mean position, right extreme position, left extreme position. So left extreme position, the value of v is equal to 0. Right extreme position, again the values of v is equal to 0. So and the maximum displacement for mean position is 0, mean position 0, and left and extreme position left extreme and right extreme position is plus or minus a. So at x is equal to plus or minus a, v is equal to 0. To find the value of c, that is constant of integration, that is at x is equal to plus or minus a, v is equal to 0, this is the condition. So substituting above condition in the equation number 2, so equation number 2 is the v square by 2 is equal to minus omega square x square upon 2 plus c. Okay, therefore the value of v is equal to 0, therefore v square by 2, this quantity is 0. So 0 is equal to minus omega square a square by 2 plus c, or c is equal to omega square a square upon 2. So substituting the value of c in equation number 2, so this is again equation number 2, v square by 2 is equal to minus omega square x upon 2 plus c. So v square by 2 as it is, then minus omega square x square by 2 as it is, plus the value of c is equal to omega square a square upon 2. So 2 get cancelled, so equation becomes v square is equal to minus omega square x square plus omega square a square, or v square is equal to, take omega square is common factor, so omega square is equal to in bracket a square minus x square. This is the same example. So v square is equal to omega square a square minus a square. If you now the squaring both sides, so v is equal to omega, this is a value omega, this is a plus or minus, therefore v is equal to plus or minus omega square root of a square minus x square. This is equation number 3. So this equation represents the instantaneous velocity or the velocity of the particle which perform the simple harmonic motion. So this is a very important equation, v is equal to plus or minus omega a square minus x square, and this is the velocity of the particle which perform the simple harmonic motion. Another example is the expression, another point is the expression for maximum and minimum velocity and expression for displacement in linear harmonic motion. So the maximum and minimum velocity, as we know that velocity is equal to plus or minus omega a square and square root of a square minus x square. So case number 1, at the mean position, as we know that the x is equal to, that is displacement is 0, so velocity v max is equal to plus or minus a into omega, and extreme position the displacement is plus or minus a, therefore v minimum is equal to 0, because at this point the value of a is equal to 0, this therefore this quantity becomes 0. This is the summary, again the same example. In this case, the left extreme position, the value of x is equal to minus a, right extreme position, the value of x is equal to plus a, at mean position x is equal to 0, therefore a max is equal to plus a omega square, and right extreme position value of a max is equal to minus a omega square. At the point x, the value of a is equal to minus omega square x, and at mean position the value of a minimum is 0. And this is the summary of velocity of the particle which performs the simple harmonic motion. So at mean position x is 0, a minimum is 0, therefore v max is equal to a omega, and left extreme position the value of v minimum is 0, and right extreme position the value of v minimum is 0, and at mean position the value of v max is equal to a into omega. Now this is the expression for displacement. As we know that v is equal to omega into square root of a square minus x square. So as we know by the definition of velocity, v is equal to dx by dt, therefore the v is equal to dx by dt, which is equal to omega into a square minus x square. So omega into dt, which is equal to dx upon square root of a square minus x square. So integrating this equation, then integration comes. The integration dx upon square root of a square minus a square, which is equal to integration of omega dt. So integrating both sides, we get the dx upon square root of a square minus a square omega into dt. This is a formula which are used to formulate the integration. So integration of dx is equal to x plus c, integration of dt is t plus c. Okay, then therefore integration of dx upon a square minus a square is equal to omega integration of dt. So integration of dx upon a square minus a square, which is equal to the integration of omega into dt, is nothing but the sine inverse x upon a plus c. So sine inverse x upon a is equal to omega t plus alpha. So where alpha is the constant of integration, which depends upon the initial conditions. It is also called as epoch or initial phase angle. Okay, this alpha is the initial phase angle, where alpha is the constant of integration, depends on initial conditions. So x upon a is equal to sine of omega t plus alpha. So the final equation is x is equal to a in a into sine omega t plus alpha. X is equal to a sine omega t plus alpha. So this is the expression for displacement of particle which performs the linear simple harmonic motion, which is very important. X is equal to a sine omega t plus alpha. But in special cases, that is case number 1, the particle start from mean position. At this position, the time is 0, x is equal to 0. Okay, therefore if we put this value in this equation, then 0 is equal to a sine as it is plus omega t is the value, t is 0, t is 0, therefore omega t is equal to 0. So 0 plus alpha, so 0 is equal to a sine alpha. So sine alpha is equal to 0, that is alpha is equal to 0. So alpha is equal to sine inverse of 0. So alpha is equal to 0 and x is equal to a sine omega t. So this is the equation of simple harmonic motion if the particles start from mean position. So at mean position, the x is equal to a sine into omega t. In case number 2, particle starts from suppose extreme position. At this point t is equal to 0, but x is equal to a. This is where a is the amplitude. So if we put the x is equal to, then a is equal to a into sine 0 plus alpha. Okay, so a get cancelled. So 1 is equal to sine into alpha, or alpha is equal to sine inverse of 1, or alpha is equal to pi by 2, because sin pi by 2 is equal to 1, therefore alpha is equal to pi by 2. So sin pi by 2 plus theta is equal to cos theta. Okay, so x is equal to a sine omega t plus pi by 2, or x is equal to sin pi by 2 plus theta is equal to cos alpha. Therefore sin pi by 2 plus omega t is nothing but the cos omega t. Therefore x is equal to a cos omega t. So this is the equation of simple harmonic motion of the particle which starts from the extreme position. So the another point is discussed on our next lecture. Let us summarize the expressions. These are the differential equations of linear simple harmonic. First is the differential equation of linear simple harmonic motion. So d square x upon dt square plus omega square x is equal to 0. This is the expression, differential equation of linear simple harmonic motion. The expression for acceleration simple harmonic motion is the expression of acceleration. So the acceleration is equal to a is equal to minus omega square x. So these are the two cases at x is 0 and x is equal to plus or minus a. And the expression is that the acceleration is equal to plus a omega square for left extreme, right extreme a max is equal to a omega minus a omega square. And the velocity, values of velocity is an in summary. This is the acceleration, and this is the velocity. So velocity minimum for left extreme is equal to 0, right extreme is equal to 0. At mean position, Vmax is equal to a omega square, and at point P or at a displacement x, the value of V is equal to plus or minus omega a square and square root of a square minus x square. Then the expression for displacement. Now the expression of displacement is x is equal to a sine omega t plus alpha. So in these cases, the value of x is equal to a cos omega t and a sine omega t for case number 1, that is at mean position. The value of x is equal to a sine omega t, and for extreme position, the value of x is equal to a cos omega t. So the remaining part we will discuss in our another lecture. Thank you.